It was going guys, xiangqi here, so we've come to the moment of truth. So in this video we're going to be making moving and making them back recursively to ensure that engine actually is capable of searching. So even though it's not returning any decent evaluation at the moment, but at very least it does so-called the brute force move through traversal. So it goes through all of the possible positions within a current given depth. And I'm going to be demonstrating how this works in this video. So probably I would start with the depth 1. So you can currently try to search with the depth 3, but let's consider depth 1 for now. And I assemble and upload. So let's have a look at the hex dump before we did anything. Actually 0.16. So here and down here we have our board position, and let me just quickly check whether I did consider breaking on make, move, and take back or not, because that's essential to demonstrate. Yeah, I didn't, because that's essential to demonstrate. So if I just run this and nothing happens, this won't impress you, I know. So let me try to demonstrate this with bells and whistles. So again, assemble, upload, hex dump. So here's the starting position. Now I'll make a move. So go to 0, 2. Am I typing something? Okay, 0, 2, 0, 0, and I made a move. So let's have a look at the hex dump. So the pawn goes from here to here. Then the next, it would break after taking the move back. So if I say 0, 3, 1, 5, 0, 3, 1, 5, go, hex dump, and I drop the pawn back. Now the next move would be considering double pawn push. So zero, 3, 0, 3, 4, F, I believe. I'm not sure if I did consider the address properly. Hopefully I did. So let's make sure if I really did. Yes, and indeed we have a double pawn push. So if I would be proceeding this way, would it be this pawn like single push, double push, single push, double push, etc. But it's incredibly long to wait that way. So let's actually get rid of the break and here the take back. So we only inspecting the board position where the new move has been considered. So just reassemble, upload. Hex dump. So we get a pawn push, and the next snapshot of a board state would be pawn already in the next in a position of the next move. So 0, 0, 3, 1, 5, and run. Hex dump. Let's say like already is here. Then the next move would be here. Just try and demonstrate you that. So 0, 3. 0, 3, 1, 5, and here we go. And we have this move. The next one would be double pawn push here. So 0, 3, 1, 5, hex dump, and so on. So just trust me that it goes for all of the pawns, and then the knights going like left, right, left, or right. But it's not really that impressive so far, because we're not doing any recursion. So I could have made this using just the bare static variables, like the global variables. But we're using the stack in order to save the whole lot of local variables for source square, target square, capture p, step vector, a whole lot of things up to 12 variables that has been covered in this series in great details. So before I run, before I increase the depth, before I increase the search depth, I just want to demonstrate what happens if, so how I test this basically. So I just temporarily remove the break from here and assemble and upload. So the program is going to be make move, take back, make move, take back, make move, take back, make move, take back, and so on until it runs. And eventually, if make move and take back works properly, this means that the position that we came up with initially should be exactly the same position after the program completes. So again, like uploading 0, 0 to 0, 0 and run. And it goes instantly because it's quite fast on the depth one. So go into the hex dump, and we see exactly the same board position as before, which means it didn't mess up anything. Okay, so far so good. So I uncomment this break on make move, and now let's go for a bit more interesting experience. So we'll now increase the search depth to 2, which means it would be making a move by white, and then it would be responding with black, all the possible responses with black. So let's go for a search depth equals to 2 and assemble and upload 0 to 0 to 0, 0 and run. So go into the hex dump again. So now we made a move, but the next it's depth 2, so it would be responding with all the possible pieces. So the next move, this knight should be responding here. So let's have a look if that works. So 0, 3, 1, 5, and we go in hex dump. And indeed, we have this knight going here. So the next move, it would be going here. Let's inspect that as well. 0, 3, 1, 5. And hex dump. And knight goes here. And it would also go for this knight, all the pawns, and then it would take this back and consider next move. And this is how it would traverse all the search tree. So it takes longer, and just to demonstrate how this is going to be working with how is this going to be working for real, I just get rid of this break and assemble and upload and run. And now it takes a little bit of a time, so the display is flashing up because it takes a little bit of time to calculate. And now to make sure that we didn't mess up anything, the position is still the same. We just checking out the position, and position is the same, which means that the mode generator didn't mess up anything. Now the most interesting part, so I uncomment this back. And now we have the depth 3, which would be the working depth for the engine, because less it's too weak, more it's too slow. So it's sort of a trade-off. So let's consider the depth of 3, which means the following. So white makes a move, black's response, and white makes all the moves in response, and black another response, and so on. So it's really easier to demonstrate rather than to explain. So let's go for this. Upload 0 to 0, 0 and run. So here we got first move, then black would respond. So 0, 3, 1, 5. Now black responds. Okay. 16. Now say like black responds, and now white is going to be responding. So the next move, this pawn would go here. The next move, this pawn would go here, etc., etc. So let's have a look how this works. So 0, 3, 1, 5. Okay, hex dump. And indeed, the pawn goes forwards. Then this pawn would return back, and this pawn would go here, because that is the next response. So 0, 3, 1, 5. And 0. And indeed, this pawn returns, this pawn goes forwards, and so on. And just to make sure that this would be done recursively, and it all makes all the moves, it takes all the moves back. Eventually, after the end of this function call, it should return to the original board position. So let's check that as well. And that would be the last test for today. So for that purpose, I just need to command out this break again. To command this break. Right? Yeah. And assemble and upload 0200. And now this takes time because this is about the natural speed of 6502. Well, more or less about the same as the Realkin one. And it takes time to get the best move to search to the depth3 to traverse through all of the leaf nodes, and there's quite a lot of moves. It's more than 9,000 positions eventually. There is information at chessprogramming.com. Sorry, just program Wikipedia. I'm not sure what the address exactly is, but it doesn't matter. So one last hex dump here, and you see, like, after depth3 search, we have exactly the same position. Nothing messed up, which means that our mode generator most likely working properly. And also, I've been trying to put a piece, like, to capture, test it with a capturing a piece, so that I make sure that the capture piece gets restored. So probably, yeah, let me show you that on the depth one. Actually works on whatever depth, because it just fetches the capture piece from the stack from the specific depth. But just to give you an idea, because this is something where the bugs are occurring in chess programs. So for instance, we put a pawn here, and for instance, we still want only the depth one, just to make it faster, basically. So let's go to depth one, and assemble, upload 0200, and run, and hex dump. So now the first move, excuse me. Oh, that's because, okay, that's because there is no break. So I need to make the break work. Yeah, now this will work. You saw that the piece was restored where it initially was, so it kind of works. But just to give it a little bit more visual understanding how this works, go into hex dump. So first, yeah, all right, it first goes up. It first goes up. So 0315, 0315. Then probably it's a double comp push. I'm not sure, but let's make sure that is the case. Hex dump 16. Yes. No, actually, yeah, it is. So now it's double pump push. So the next one is hopefully going to be the capture, because, yeah, I don't actually remember how it was so far, but let's have a look. 0315. Hex dump. Should be working. Okay, great. So now this pawn captures here. Okay. And the next move would simply be this pawn to one step ahead, and this black pawn that is captured is going to get restored. So let's figure that out if that is the case. 0315. Okay. And indeed, so this pawn moved back, the capture piece has been restored, and then the next piece is actually moving. So this kind of works. And yeah, it's not because I'm so smart, I'm not as big. That's because Hartgert Müller has an absolutely fantastic implementation of his micromax that I've simplified a lot. And here I made a prototype in C, and then I just translated this to assembly, and that's the reason why it works so easily. But anyway, I was never implementing this stack frame based variables, like local variables, literally, and here is like up to 12 local variables, just to give you an idea. So here are all the local variables that are mapped to the stack, and yeah, all this works recursively. And this is kind of moment of truth for me, guys, because this is really like, you know, like all the effort I put so far. Now, like the major amount of work is done. The major result is already achieved. So I now only need to write an evaluation function and make sure it returns the proper scores. And in that case, actually the program would already be able to play chess and I really hope to fit into 1K, like 1024 bytes. because I still have a whole lot of free space after the 0 page ends and on a stack page on its own, because not all the stack page is used, but just somewhere to here. I'm not sure. It's like 12 multiplied by 3 plus it's 48 plus starting addresses. So yeah, it's around 50 bytes are used on stack and the rest is free. So we're gonna make use of that as well. Well, I guess this is it from my side. Thanks for watching. Until the next time, and take care.